What gives particles its mass? Well, since the discovery of the Higgs particle in 2012 and the Nobel Prize presented to Peter Higgs and François Englert in 2013 for the proposition of the Higgs mechanism in 1964, the answer seems to be clear. The Higgs field does give particles what we experience as mass. But where does the Higgs field actually come from? Shouldn't a combined theory of Einstein's general relativity and quantum theory give the answer? It is widely assumed that Einstein's general theory of relativity cannot be combined with quantum theory. At least so far, nobody has found a truly conclusive way. In this presentation it will be shown that A. The job was in principle already done by no other than the German mathematician David Hilbert. B. There is no need to combine quantum theory and general theory of relativity because the latter already contains the first. And C. The Higgs field is one of the possible outcomes of such a theory, but it also comes with a little surprise. Its existence, namely, seems to require an exponentially growing universe. A theory of everything for which we are aiming here should not only contain Einstein's general theory of relativity, but also all major quantum equations, and it should also explain the appearance of what we describe as matter. In this presentation, we will concentrate on the quantum gravity derivation of the so-called Higgs field. Due to its peculiar shape, it is sometimes also called the Mexican hat field. Our starting point is the so-called Einstein-Hilbert action, a variational integral based on a Hamilton extremal principle. Already in 1915, it was the great German mathematician David Hilbert who derived Einstein field equations from such a fundamental minimum principle. What Hilbert apparently did not see was that his formula in fact contained much more than just the Einstein field equations, but that he had also found the fundament for quantum theory. In this presentation we will now show what Hilbert had missed, or, taking Hilbert's genius, simply not considered important enough to be mentioned at all. In our previous presentations, especially C part 1 of the series, we have shown that we do not need the matter term Lm to obtain matter. And so we had always set both lambda, which stands for the cosmological constant, and Lm equal to 0, and just proceeded with the curvature of spacetime, known as the Ricci scalar, as the kernel within our variation. Now, by following Hilbert's classical derivation, we obtain the so-called vacuum Einstein field equations. Obviously, these equations do not contain any matter. Things change, however, in a rather interesting manner when introducing a slightly adapted metric tensor with a scaling factor as shown here. Hilbert's variation then yields a much more complex kernel. At first, we split up the variated contravariant metric tensor into its scaling and its tensor part as shown here. As a result, we obtain two equations, a scalar and a tensor one. For the time being, we ignore the tensor equation, for example by assuming that the variation of the metric tensor gives 0. Then we intend to fulfill the scalar, which is to say the first equation, by demanding the kernel of the integral to be equal to 0. This gives us the following partial differential equation, and by inserting a certain setting for the metric scaling function capital F of f, we automatically end up with a function of clear Higgs field type. In the case of vanishing Ricci curvature r equals 0, we obtain a wave equation with a typical solution as shown here. Unfortunately, this solution does not really make us happy for a variety of reasons. We leave it to the interested listener to find a few of them. Much more interesting solutions appear the moment we allow for a non-vanishing Ricci curvature. In the case of negative curvature, for instance, these solutions give peculiar oscillations which are due to the square occurrence of f in capital F, summing up to a simple periodic scaling behavior of the metric tensor. We cannot overlook the fact that the behavior of these solutions are similar to the particles at rest. For this, we refer to our fifth part of the series. Here, however, it serves as a universal scalar field with the correct markings of the Higgs field. For positive curvature, we obtain exponentially growing universes with a funny behavior near the Big Bang, where we find a non-zero scale at t equals 0, followed by a decreasing scale and a non-zero minimum after a certain time t equals t0. With a scenario like this, our universe would never have been squeezed to a point, but always would have had a certain size. Even at its minimum, the universe would not be a mathematical point, but an entity of a distinct size. Surprisingly, this minimum size is connected with the Higgs field in the case of negative r. This automatically brings us to the suggestion that perhaps the total curvature in fact does vanish, but that there is a negative r which leads to oscillating solutions and thus particles, or as considered here, a universal Higgs field and a positive r of equal size that gives the exponentially growing universe. Here we would have a rather constructive zero of r minus r, namely one which would have made our whole universe, which is to say its matter, its mass-making Higgs field, and its expansion. In fact, so it could be assumed with the information at hand and the obvious observation that our universe appears flat on bigger scales, without the expansion we would neither have matter nor mass. But there are more possibilities, even some which do not require a Ricci curvature at all, not even an effectively vanishing one. When going back to our extended, which is to say scale-factored Hilbert variation integral, and bringing the tensor and the scaling part back together, we suddenly see that even in a completely flat space-time, meaning where all r terms are vanishing, we can still have a scalar equivalent for our Ricci r in order to, hopefully, obtain the necessary particle, Higgs, and or scaling expansion conditions. We only need to remind ourselves that the tensor part under the integral has to be summed up with a contravariant variated metric tensor, and this just gives a scalar again. And we are comfortably back with the right equation for the metric creation of particles, Higgs fields, and or exponential growth. For completeness only, we here also give the unabridged form of this equation. By inserting what we know about our scaling function capital F, we end up with an equation completely depending on the inner wave function f, its variation, and the variation of the contravariant metric tensor. There too could be an intelligent or constructive zero assumption when just playing with the variational terms, which is to say that the delta terms appear positive and negative and effectively sum up to 0. But this they don't do without before being used as substrates for both matter, Higgs fields, and exponentially scaling growth. It should be pointed out, however, that there are also other options to metrically derive matter fields and potentials via additional dimensions. The interested reader may find more information in the books shown here or other publications of this author. We explicitly want to point out here again, however, that we do not consider us the first to have found the connection. In principle, namely, it all was already inside Hilbert's ingenious approach, and he only could not see it because, at the time he wrote down his equation, the fundamental equations of quantum theory were not yet discovered, and his main goal was the derivation of the Einstein field equations, and thus As Einstein had not bothered about also finding quantum equations inside his general theory of relativity, Hilbert, as a mathematician, obviously saw no need to consider the broader spectrum residing in his approach. These new insights open up a variety of possibilities for the most astounding developments, be it inexhaustible sources of energy, future weaponry, metric artificial intelligence, quantum gravity computing, or completely new, and what is much more important, truly unbiased and most holistic modeling tools for almost all sorts of problems. And how could such developments be realized? The optimum is the global approach aiming for the quantum gravity computer and naturalized AI, which is a Manhattan-sized project. How this disrupts everything and makes the owner the global monopoly to just everything can be extracted from the material presented in this talk. Next smaller step is just the naturalized AI, which still is a small Manhattan project. This too already reaches very far and propels the owner into a global monopolistic and long-time leading position, unless somebody achieves a takeover via a working quantum gravity computer tech. Everything else are service projects.